Okay, so thanks so much to the organizers for inviting me, and thanks for everyone for making it to the very last session on Friday. I know it's not easy, so thank you for being here. And today I just want to talk about some work that I've been doing together with my student Giorgio Pizzolo and also Javier Peraza, who is starting a postdoc at Perimeter. And it's based on these two papers and also some work in progress. And in particular, the gravity stuff is in progress. I would appreciate comments and thoughts on that. But before, I couldn't help myself because in the last few days, we've seen so many talks on self-duality. So I just wanted to take one slide, just a quick ad for this paper that we put out recently that unfortunately I won't have time to talk about because I felt it didn't fully fit with people's interest here. But basically the idea is of using these homotopy algebras, these generalizations of algebra, for better understanding how to project information to null infinity. And there's this kind of hope that it will help with having a more formal or at least a slightly different understanding of holography. And also for those interested in double copy, it gives a very nice way of constructing kinematic algebras in slices near null infinity. So if you're interested in these topics, have a look. This is also with my student and another collaborator, Felipe Diaz-Jaramillo from Humboldt. Good, so the structure is the following, and I'm not sure how much I'll have time to go through, but first I'll just quickly review the sub and leading soft theorems, and in particular how they come from symmetries, and then issue that arises when we try to do it from the symmetries. Then I'll introduce this trick for resolving that issue. Then after the trick, we'll see that there's some new fields. So all these infinite modes that enter, I'll show you how to put these in a Lagrangian and construct charges. And then finally, what the algebra of that charges is and how it may relate to holography. And then I'm not sure I will have time for this final bit, but if I do, I will say a little bit about how these symmetries can control soft limits that do not have quite universal behavior. So things that are a little bit surprising compared to what we normally think of how things work. Okay, so just to start with an overview. So for some of you, this may be very, very familiar, but just a quick overview for those who haven't seen it before. So the soft limit, of course, is this idea that I take an amplitude. This one is for gauge theory in particular. I let one of the particles go soft, and then at leading order, I will have this nice factorization. There will be a pole here, and this is the amplitude for all the other legs. And the way we understand them from the symmetries is that we go to null infinity and Bondi coordinates, and then for a gauge theory, we have this nice kind of just a gauge parameter, but we don't let it fall off at infinity as we normally would, but rather it has this dependence on the z and z bar coordinates. These are the ones that kind of parameterize the celestial sphere. And then we transform the A, and this, just to kind of, this will be important for later, this will preserve the fall off. So you see, this is how the gauge field fall offs as I go to null infinity. This is just from basic physics considerations. And this is how the gauge symmetry kind of preserves the fall off of this leading term. Good, so then there's this result that has started a lot of further work more recently, but the result itself is quite old. But the fact is that we can take this symmetry at leading order, and via word identity, we can construct a charge and prove this soft symmetry. And then there's a similar thing for gravity. So here I won't go into the details, but the leading order thing here is something called the super translation. So just in a very similar way, from a symmetry of gravity. So now we're looking at diffeomorphisms, and the diffeomorphisms that preserve the fall off, they will give us the super translations when I take the soft limits. Good, so now let's look at sub-leading effects. So conceptually, the idea here is that I take one of my legs to be soft, but I don't fully send the energy to zero. Rather, I just send the energy to be very small, and then I do a series expansion in that energy, right? So then I have this leading order term from before, but I also have a term that's omega to the 0, then I'll have omega to the 1, and so on and so forth. Now, something that happens here is that after a certain, so at the first leading order, we just have this one term. After a certain number of steps in this perturbative expansion, depending on the theory, it may be 2 or it might be 1, I start encountering some terms that are not universal anymore. So what do I mean by universal? So this is a very beautiful and powerful statement, is the fact that this soft factor here multiplying the smaller amplitude does not depend on the details of the theory of the smaller amplitude, right? It just depends on the momentum of the particles that enter here, but not on coupling constants, not on details of how the interaction terms look like. Good, but so in principle, there's this kind of feeling, so this story I was telling you earlier with the symmetries giving us the soft theorems via word identity. So there is this kind of feeling in general that only the universal terms would come from symmetries. But the situation is, so there's two ways of kind of dealing with that. So there's, on the one hand, one could project out all the non-universal terms. So there are ways of taking the amplitude, hitting it with these differential operators with certain symmetries, and then they project out the non-universal terms. So this was done in the flat case, and it's also what people in cosmology do a lot of the time. So they wouldn't see often these non-universal terms. But something else that I don't know if I'll have time to talk about, we'll see, but that sometimes there are terms in here which at first sight we would call them non-universal, because they do depend on the details of the theory, but sometimes they can still come from symmetries. So this is just to kind of emphasize that the symmetries could be quite important. Good, so now let's kind of focus a little bit more on the subleading, on the next one, so starting just from QED. So this was the leading one here, the subleading one. I'm guessing a few people will be familiar with this, so this will depend on the angular momentum. But now we try to derive it. So remember this first one, the leading one, came from a symmetry where the parameter was just depending on Z and Z bar at null infinity. And then it was shown that for this next one, it turns out that you need a gauge parameter. And I don't know if this yellow highlighting here is actually obscuring that you can't see it so well, but that's a factor of R there multiplying the lambda 1. So maybe you can see it. Yeah, so there's a factor of R, so it's a gauge parameter that's linear in R. But unfortunately, okay, unfortunately, this will violate the fall off of the gauge field. Because remember we said from physical considerations, the gauge field itself, when I go to null infinity, it has to start at order R to the 0, and then it has lower and lower powers in R. So this violates the fall off. So the point is that it cannot be a symmetry of the gauge field itself. So if I go here, we're sort of generalizing the problem. So I want to allow, so this is with a view towards Yang-Mills, and in certain gauge choices, we sometimes have log terms appearing as well. So I want it to be as general as possible. So let's assume we have a gauge field with some finite fall off. So I've taken my gauge field and expanded it in all powers of R and also all powers of log of R, such that it doesn't blow up when I go to infinity. And then let me move to the other side because I can see better from here. Then I do the same for the gauge parameter. So for the gauge parameter, I'm assuming this is called a polyhomogeneous function. So I have something that's, you see different powers in R, different powers in log of R. And these kind of gauge parameters are such that they will be divergent when I go to null infinity. And I think in the next talk, you may see things that depend on logs, which appear at loop level. There's a further generalization in the paper that I think it looks a bit too ugly for slides, but in certain gauges, when we look at these soft theorems, it can happen that the parameter itself is also field dependent, but I won't put it on the slides because that's a bit too ugly. And then there's a similar story for gravity as well. Good. So we have this issue. So we have this issue that we have a certain fall-off here and kind of the opposite fall-off here. So this lambda, remember, cannot be a symmetry of this gauge field. So it turns out that it's helpful to think of this as a symmetry breaking, in the sense that I have this symmetry, I can't realize it on the A. So when I have a symmetry breaking, I can invoke this Stuckelberg trick. And for those who are not familiar with it, this was actually, it first appeared in massive electrodynamics, but it's since been used in cosmology as well and in a few other contexts. So here we will use it for the purpose of taking this gauge parameter, so this lambda plus with the funny fall-off. And the trick, it goes the following way. So you take the gauge parameter, you promote it to a field where the field has the same properties as the gauge parameter, in the sense that it has exactly the same fall-off as the parameter did. Okay, so now we've extended the phase space. So this is the boundary condition. From just having this would be just the gauge field. Now we have all the coefficients that appear in the expansion of this psi here. And this psi is a Goldstone type field, which we will see shortly from its transformation properties. Good, so what do we do with it? So we take our original gauge field A, and then we dress it with this psi that we've introduced. So the way we dress it is by following the symmetry rules, right? So if you look at this expression, this looks just like a symmetry transformation, right? Like the general symmetry transformation in Yang-Mills, where now I've, instead of putting a gauge parameter here, I'm putting this new field that I've introduced. And then the consistency condition that we require is that this dressed field, so this thing we call A tilde now, transforms just like a standard gauge field. So this is like all levels in lambda, and this is at linear level in lambda. Where now I want to combine, so lambda 0 is the thing from the leading order, and lambda plus are all the overleading things. So the key point is that the transformation of A is unchanged. So A still just transforms with the parameters that preserve its fall-off, but all the lambda plus transformations are now absorbed in the transformations of the psi. Good, so then we can just derive what the transformation of this is going to look like. So we have our A, which is dressed like this. Remember, we had the consistency condition on this slide here. So from this, one can work out how the Stuckelberg field, so this S is like the exponential of the Stuckelberg field, one can immediately work out its transformation rule. And then these are more like details, but if I then want to go at linear level in lambda, it depends on this kind of operator. So this is the adjoint here. One can formally expand this to all orders. So this is the transformation that one would put into the charge algebra. Good, so this is also this is what the expansion looks like. It's not very important at the moment. These are called the Bernoulli numbers that appear when you expand these kinds of operators. So the important thing, so remember we're saying this is a Goldstone type field, is that at 0th order, these psi's transform just with a shift. So once you expand this slightly ugly looking thing, the first term here, so 0 here means 0 order in the field, it's just a shift like for a Goldstone. Good. There's something else we could do that is actually useful for the purpose of writing the Lagrangian, and that is to do a full Stuckelberging. So remember what we did before. So we had this dressed gauge field such that the gauge field itself only transformed with the 0th order parameter, and then the psi transformed with the overleading parameters. But now that we've allowed ourselves to do that, we can take one step further, in fact, and just do this other type of dressing where the gauge field now doesn't transform at all, and I've moved its transformation entirely to the psi, and now the psi has an extra component here at 0th order, so it transforms, it's completely absorbed into the dressing. So this is useful when we write Lagrangians later. Good, so for GR, so just to show you something in progress for GR and how we think one should think of this on the GR side. So recall everything came just from things that look like the gauge transformations of the field. So for GR, we would just write the Lie derivative here. This is not sufficient. So a thing that was important for Young-Mills was that we had this psi here, this dressing written as the full gauge transformation rather than just a linearized. So notice we didn't just write a mu plus d mu psi. So this is because we're trying to capture effects at all orders in R. So there may be a mixing between different orders. So you want to keep everything and then at the end truncate to whatever order you want to work to. So the point is that this Lie derivative transformation that we usually use in GR is not sufficient here. Ideally, we would want to do something that start with something that looks like a full general coordinate transformation, but notice that this one is not great because the coordinates here are not the same as here. Also, we like to have something that has some nice expansion. So we work with this. So it turns out that when you do a coordinate transformation of this type, so this is called a one parameter family of diffeomorphism. So for some vector psi, if I transform the coordinates like this, then the metric transforms like this to all orders. So this is the one that we think is the right one to use in gravity. And then we take the procedure and we just apply it like we did for Young-Mill. So what we do in gravity here, we take the G, it's dressed in the same way where you see I've replaced this psi here, which was the diffeo parameter. I've replaced it with a vector V, which is now my Stuckeberg field. Good, so now I'm going to try to do the full Stuckeberging because it actually turns out it's simple. One can also split them. So remember for Young-Mills, we had two different possibilities. Let's do the simpler one where I want the metric to not transform at all, and then all the transformations to be absorbed in the Stuckeberg vector. So then the consistency condition is that this dressed guy, just like in Young-Mills, now it transforms in the standard way, and then you can immediately work out the transformation. So it looks something like this at all orders, the transformation of the Stuckeberg vector in gravity. And then at perturbatively, again, you can write it in terms of this curly O operator here. And if you expand that, you again see that it's of a Goldstone type. So it starts with a shift, and then there's higher orders. And all these higher orders, I mean, maybe the subject looks a bit exotic, but once you expand it, it's just a sum of commutators. So in the Young-Mills case, it was just the sum of commutators of the Stuckeberg field with the parameter. For gravity, commutators are just Lie algebras of the Stuckeberg vector with the diffeo parameter. So it's not as bad as it looks. Good. So now that we have these symmetries, we want to construct some charges with them, and we want to look at the charge algebra. Good. So immediately we run into a sort of issue, which you might have predicted from seeing how I've dressed things, right? So if I take just my pure Young-Mills action and I dress it with this field psi, the field strength will just look like this, right? So just like how the field strength would transform in Young-Mills, but with psi instead of lambda. So now you see, if I look at this Lagrangian, it's actually identical to the original Lagrangian. This will drop out basically because it's gauge invariant. So there's kind of two ways to think about it. So the way we originally thought of it, and it turns out that it coincides with the second way, is to just take A tilde as a package and consider A tilde to be a field and then construct the charge for A tilde. So the first one, I don't think I will have much time to describe the covariant phase space formalism. So for those who are not familiar, it's just a more sort of fancy version of the Noether procedure for constructing charges. And it turns out that in certain contexts in GR and when looking at asymptotic charges, it turns out to be a little bit better. It gives us a bit more control than just a Noether procedure. So the way it works is you take the Lagrangian, you vary it, you get this theta. From theta, you construct something called a symplectic form, and then that will give you the charge immediately. So you just take some commutator of transformations, and then this omega itself becomes a total transformation of an object, which will be exactly our charge. So I rushed that a bit, but if people are curious about the covariant phase space I'm happy to talk about it more later. So from this formalism, we construct a charge, which if you ignore the yellow part from here, should be familiar to people who have looked at asymptotic symmetries, because this, without the zero here, is just the leading order charge for the leading order soft theorem. What the zero means is that now I have more ingredients in my charge, but I am taking only the zeroth order in the radius kind of part of this. So remember, this F tilde has a bunch of psi's which have overleading powers in R. So remember, this F tilde was defined as containing these psi's. And then this lambda also is now allowed. So the gauge parameter lambda is now allowed to go to all kinds of higher powers in R. But from that, we take just the zeroth order part. And you might, okay, thanks, I'll be done in 2 seconds. So you might ask whether one is allowed to do that. It turns out there are ways of renormalizing by using the ambiguities of these objects that appear in the phase space formalism. Good, and something that I haven't explained, but just to touch upon it quickly, because you might wonder, so the subleading soft theorems are an expansion in energy, right? And I was showing you parameters that are higher and higher orders in R. And it's actually the U coordinate, which is like the time coordinate at null infinity, that's inverse to the energy via Fourier transform. Well, it turns out that there's a way, when looking recursively at these via the equations of motion, there's a way of seeing that when you go deeper and deeper in powers of R, you extract higher and higher powers in this U, which is a Fourier transform to the energy. Good. So this, again, one has to really look at the soft theorems and how one derives the charges, but just to give you an idea, there is a connection between the R expansion and the U expansion, which is what you would naturally expect for subleading terms. Good, but I wanted to show you quickly, so this was not in the original papers, but there is a better way of writing a Lagrangian for these modes, right? Because the fact that we got a non-trivial charge, so we got this charge that does depend on the Stuckelberg fields, so the psi does not drop out here, means that there should be a way of seeing a Lagrangian, seeing a space where these psi's really live naturally. Good, so again, this is just a reminder, so this was what was happening when I Stuckelberg. This is a symmetry, so it goes back to itself. And it turns out the issue is, and this is actually a good thing, it turns out that what we were missing is the boundary terms. So it turns out these psi's, they will want to live on a boundary Lagrangian naturally rather than in the bulk. So what we do as a starting point, so we start with, again, the standard Young-Mills, then I couple this source term, which notice it's slightly different from the standard source term that you would write in Young-Mills, because it turns out to be the boundary value, not for the equation of motion, but just for star F. So this J is like a 2 form. Good, and then you take this object with a boundary, you apply the Stuckelberg trick on it. Again, the bulk part remains unchanged. However, the boundary part is now changed. So we see our Stuckelberg fields, remember this S is the exponential of our Stuckelberg fields, now living on a boundary Lagrangian. Good, so the charges, so the nice thing, which is a nice sort of sanity check, is that the charges are the same as they were before, and the way we were constructing them before, but now they arise exclusively from the boundary, from a boundary Lagrangian, which if you have kind of hopes for some kind of holography, it's always nice. Good. Okay, and just to end in the last minute, I won't show you the details of how the calculation was done, but once you have these charges, you can then construct a charge density from them. They have some nice recursion relations, and these of course generate these overleading symmetries, and now we can use them to compute a charge algebra. So the charge algebra, this is the final slide. So the charge algebra This is at some order n, sub n leading. This thing at the top tells you the order in the Stuckeberg. These are just the coefficients in the expansion of lambda, and it looks something like this. So I wanted to put it a little bit in context with things that have been done before. So in the self-dual sector for Yang-Mills and gravity, we have these infinite symmetry algebras, which have been related to OPEs in celestial holography, the W infinity here, something that's sometimes called the S algebra here. And these have been observed by many different people also in the room from many different perspectives. And what we have done, so the way we have computed our algebra is most similar to the way that this was obtained by Laurent Friedel and collaborators. So they also did it from the charges, but restricting to a certain holomorphic subsector. So our calculation would be like a generalization of what they did there. And this is the kind of algebra that you obtain, thanks, when you look at the full theory, kind of mixing all orders in the subleading expansion. For gravity, we don't have it yet. And these are some of the things that we would like to understand better. So maybe I'll stop there because I'm out of time. Thank you.